Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with more thermodynamics. We'll cover these topics today. What is equilibrium in terms of different types of it? Equilibrium state of a simple system we will see considering the ideal gas, and we will develop something called an equation of state for ideal gas. Then we will see what are path variables, especially the work and heat. Then we will see the state variable temperature in detail and what is Maxwell-Boltzmann distribution. Once this is covered, we will see about some of the important ideas as we go ahead. That is, one is heat capacity and internal energy. We have described already what is an equilibrium state. It has no change with respect to time, and each stable state corresponds to a set of conditions or state variables. But there is more to this equilibrium. There is something called mechanical and thermal equilibrium. Consider the gas here in this gas cylinder piston system. It is under a pressure P. It is acting from the inside on this piston. You can imagine like that. And there is some load on top of that. So it will be exerting some force downwards. So if this piston is in this location, it is actually balancing these two different pressures, right? So it means the pressure from inside is equal to pressure from outside. P internal is equal to P external. Only then it can remain in balance. So that means there is no movement of piston and no work exchange. If the piston moves up, it means the system does work on the surrounding. If the piston moves down, it means the surrounding does work on the system. If the piston is stable, it means that there is no work exchange. And this is called mechanical equilibrium. What about temperature? If the temperature inside and the temperature outside, if these two are same, T internal is equal to T external. If that is the case, there will be no heat exchange. If both the temperatures are same, there will be no heat exchange, and this is called as thermal equilibrium. Okay, so when we say equilibrium, we mean there is mechanical equilibrium, there is thermal equilibrium, there is also something called as chemical equilibrium. We will see about that in very detail in future. That is going to be in the heart of this course. So in nature, systems go towards equilibrium state. Once attained, they remain in equilibrium state. So since everything tries to go towards the equilibrium state, we are very much interested to figure out what is this equilibrium state. Let's consider a simple system such as an ideal gas and proceed. What is an ideal gas? It is a theoretical construct, but real gases behave similar to ideal gases except at high pressure and low temperature. So let's consider the gas, one ideal gas here in a cylinder gas piston system, and it is cold at a lower temperature. When heating is done, it expands and becomes hotter. Throughout this process, if you carefully see, the pressure remains the same. And this is called as Charles' law. At constant pressure, volume is proportional to temperature. As the temperature increases, as the gas becomes hotter, the volume correspondingly increases. Then, if we take again in the same initial state, cold gas, if we heat it, at the same time, if we remove certain amount of weight from the top, what happens is the gas doesn't get hotter, it is still cold. Meaning the energy that is supplied from the bottom is used to do some work here. Okay, in that way the energy is compensated, but the gas inside does not get heated up at all. So at constant temperature, is called as Boyle's law. At constant temperature, volume is inversely proportional to pressure. Okay, so the pressure from the top decreases, volume increases. If we arrest the cylinder piston system from moving forward, from expanding. And if we heat, then what happens? The volume is going to remain constant. What about the temperature? Increases. What about the pressure? The atoms actually will be moving faster, and the pressure, the force acting on this will be increasing. So at constant volume, pressure is proportional to temperature. This is called as Gay-Lussac's law. This is much simpler to visualize. As more and more material is added, the volume expands. Okay. So at constant temperature and pressure, so the pressure in the top is not changing. So you can imagine the temperature to be also same, the pressure to be same and temperature also to be constant because there is no heating done. But more material is added, therefore volume expands. This is called as Avogadro's law. So let's put all these things together. These are all behaviors of ideal gas. Combine them, we'll see that PV is proportional to number of moles into temperature. The proportionality constant is R here, and that is called as universal gas constant. And this is called as ideal gas law. It's a very important idea for this course. And if instead of n, small n, if we put a capital N, meaning small n, we said number of moles of atoms are added, volume is increasing correspondingly. Instead, we can think about it as number of atoms are increasing. Capital N is number of atoms, and that is also going to increase the volume proportionally. Okay, this comes from that. So when we represent this equation with capital N, instead of capital R, we are going to use K. K is again proportionality constant, but it's called as Boltzmann constant. So universal gas constant is when we use small n, number of moles, and small k we'll use Boltzmann constant when we use number of atoms. This equation is very important because it connects the state variables P, V, a temperature, number of moles. Okay? It connects all these variables. So it's called as equation of state. Okay, what is equation of state? It describes relationship between state properties. For ideal gas, it is PV equals nRT. These equations help to study the state of the system. So that's why equation of states are very important. So we are looking for the system, whether it is in equilibrium state or not, is it in a transition state, things like that. So before and after a change, we can track a system's behavior using equation of state. So we look at one state variable, temperature, in detail now. What is temperature? To understand that, imagine this kind of a volume. All the sides are L and atoms inside are moving. We can consider one atom going up and down in this direction. In this up and down vertical direction, one atom is moving. Right. Let's bring the equation of state. PV equals nRT and PV equals nKT. Both the forms are fine. Force, if we want to figure out this P, the temperature is here. We are going to figure out this side to understand what is temperature. If we want to know what is P, we know pressure is force by area. So let's start with understanding what is force. Force is rate of change of momentum, classical mechanics. So rate of change of momentum is written like this. Change in momentum over time, that is rate of change of momentum. We will figure out both of them. What is momentum change? So if you see here, momentum when the gas atom comes up is mass into velocity mv, and change of momentum is what causes the force. So this mv, it becomes minus mv as the gas reverses. Okay, so the change in the momentum is this mv minus of minus mv, that is the change, right? So it is 2 mv, that is the momentum change, right? This is the momentum change. What about the time? If you want to know the time, we know one thing about this gas atom, that is its velocity. So if we know the velocity, it comes here, it touches this plane, then it goes back all the way to the bottom plane, touches it, and then comes back, right? So it takes this entire time to travel, to go and come. Based on the velocity, we can figure out the time. 2L is the total length, as L is the side length. So total distance traveled by velocity will give us the time. Then let's bring these two dp and dt, submit them here and get the F value mv square by L. So that is the force now. This is per atom. What about n atoms? And what about atoms moving in all three dimensions? Okay. So since there are n number of atoms, we will put that here. And this is, since we are considering it in only one direction, we are going to divide the entire thing by 3. Because atoms do move in all the 3 directions. So in only one direction, we will put it 1 by 3 capital N and mv square by L. That is going to be the force of n atoms. So P is pressure is going to be force multiplied by force divided by area, and for force we derived this. For area it's straightforward, L square because side is L. P is equal to n by 3 mv square by L cubed. So that is the pressure. Then we want to have, what is this volume? Volume is L cubed. So PV is going to be n by 3 mv square by L cube. This L cube will get cancelled. So we will get n by 3 mv square. So PV equals capital N kT. That's what it is here. Okay. So now temperature we can understand based on this. This mv square looks familiar. Half mv square is kinetic energy. So this n and n can be cancelled. We can now arrive at half mv square is equal to, this 3 goes there because we are putting half mv square, that half also has to come in the right hand side. So half mv square is equal to 3 by 2 kT. So this is kinetic energy now. Now that is interesting. We got an equation which is giving us some clue about what is temperature. Let's take that and let's call this half mv square as kinetic energy of an atom is equal to some constant 3 by 2 k. We are putting it as small c multiplied by temperature. So temperature is now connected to kinetic energy. So we can say temperature is a measure of kinetic energy. It's not equal. There is a constant here. If you take it to the other side, kinetic energy by a constant is temperature. Okay. So temperature is in a way a measure of kinetic energy of atoms. Is this kinetic energy same for all the atoms? The answer is no. Kinetic energy is an average one corresponding to an average velocity. Why are we all of a sudden talking about average values of velocity? You'll get to know the answer now. Think about thermal equilibrium at atomic level. When we say thermal equilibrium, we said temperature inside and outside the system is going to be same. So there is no heat exchange. That's why the system is in thermal equilibrium. But what about the inside of the system? There are multiple atoms. If the system is in thermal equilibrium, then will all the atoms share the energy equally? Will all the atoms be moving at the same velocity? Because we are using the word equilibrium. So we tend to think like everybody has got equal amount of energy. So all atoms are moving at same velocity. Is that true? The answer is no. You can see that here. This is how atoms are moving. They are moving constantly, exchanging their energy. An atom that moves fast gives its energy, kinetic energy to another atom, and it slows down. Okay. So if that happens, then all atoms cannot be moving at the same velocity every time. So you will eventually get this sort of distribution. This distribution here in the y-axis, what we see is frequency. You can imagine it as the number of atoms. Okay, how many number of atoms is there in y-axis, and in x-axis speed or velocity is given in the x-axis. So at very low velocity you have some number of atoms. At really high velocities again you have very small number of atoms, and velocities in the middle, more number of atoms have a velocity which is somewhere in the middle. Okay, so this kind of distribution happens. This is called as Maxwell-Boltzmann distribution. So the temperature does not change when the system is in thermal equilibrium. Outside it is all one single temperature, right? There is no macroscopic change in temperature. But if that is so, are all the atoms have the same energy and moving with the same velocity? Answer is no. The atoms constantly collide with one another and exchange energy. If that happens, there will be differences in velocity. Okay. So at equilibrium, what happens is Maxwell-Boltzmann distribution. Okay, atoms move at various velocities following this sort of distribution at equilibrium. That is fascinating. Even I was thinking, since it is equilibrium, all atoms should have equal energy, but that is not so. Atoms have this sort of statistical distribution. So this is a fundamental behavior of nature. What happens when the temperature increases? Okay, as the temperature increases, the distribution shifts towards higher average velocity. You see, T1 is here. As the temperature increases to T2, which is higher than T1, the distribution changes. Number of particles against velocity. The particles with the maximum number of particles here, you see what is the velocity. That velocity is now here. Previously, it was here. For the red peak, it was here. Okay, so a more number of atoms are moving at higher velocities. So this is a fascinating quote by Peter Atkins. In the underworld of atoms, all is motion, migration and reaccommodation. The Boltzmann distribution is a dynamic living beast pulsing with internal change. It is the most probable distribution of a ceaselessly changing fluid dynamic underworld. The calm observed by an external observer conceals the storm within. A single temperature from outside, but inside there is a storm going on. It's amazing. Right. Now it's the right time to look at path variables, work and heat. Heat is straightforward because heat nothing but the energy that you supply, in the heat energy that is supplied. Okay, there is more to it. What basically heat is not even energy. Very fundamentally speaking, it is just the kinetic energy of motion of atomic of atoms and the subatomic particles and things like that. Okay, but for this course sake, we will use heat as the heat energy Q. We will represent it like Q and proceed. As far as work is concerned, there is something to discuss. Let's say we are heating a gas and the gas expands. So this is the distance over which the entire expansion happened. There was an external pressure. Against that, this work is done. So when we calculate this work, we have to use the force against which the work is done, the pressure against which the volume expansion has happened. Okay. You may think that when some force is used to do a work, force into distance will give you the work. But it is not so. The work is always done against the force. We have to use that force to calculate the work. To understand that, think about work done against gravity. Okay? There is a mass and it is, let's say, lifted to a certain height. Therefore, this the force acting down is mg, mass into acceleration due to gravity we can use. That is the force given by this mass when we lift it. So work done is against this force mg. That's the reason why when we calculate work as force into distance, we use mg as the force, which is the force against which the work is done, and over the distance h. So work done by the gas against an external pressure is what we have to calculate for this system. This is going to look similar to that. Let's see how. So here it is called work done against the external pressure. External pressure P is force by area, and the volume change is what has happened by this work, which is area multiplied by distance. What is that area? This is that area, and this is the total volume change that has happened because of this work. Okay, if we want to calculate that work, we are going to calculate P multiplied by delta V, which will give us force by area multiplied by area into distance. So these areas get cancelled and we get a structure like force into distance here. Okay. So force into P delta V is nothing but force into distance. It is work done. So work done is equal to this P, which is P external multiplied by delta V. This will give us the work. And in this case, as the heat was given, as the expansion happened, pressure was constant. But if pressure is not constant, we need to have a function for pressure. We can integrate that from whatever is the initial state to final state. With respect to V, we can get work done. So this is where equation of state can be quite useful. We can have a relation between P and V. We can use that and find out the integration P dV. So this is how work is calculated. So why do we call a heat and work as path variables? With this example, you can understand that temperature can be changed by heat and work. Imagine three different scenarios. In all these cases, we are going to achieve a same final temperature, if not exactly the same final state, at least the same final temperature we will achieve. Initial temperature in first case is T1. Let's put some weight on it and compress it. Okay. Because of this compression, the gas inside gets hotter. It goes to temperature T2. This can happen, right? In this second case, what happens is we have arrested the volume from expanding. Initial temperature is T1. Now we supply some heat. Straightforward, the gas is getting hotter and reaches the temperature T2. Now, in third case, what we are going to do is, its initial state is again T1. We are going to heat it to such an extent that it gets hotter and goes to temperature T3, higher temperature than T2. And by removing some weight from the top, we are allowing the gas to expand so that whatever extra heat, extra temperature was there, T3, has now come down to T2. So now we have again reached the same temperature here. In all these cases, the temperature is same. Okay. So to achieve certain temperature, you can give more heat and take out some work, or you can give the right amount of heat. So it's up to us. Or you can do the right amount of work. Okay. So if all these things, heat and work can be any value. Okay. Any amount of heat and work exchange can happen to achieve the same state. At least in terms of temperature, these are the same states. Okay. Heat and work in that regard are path dependent. Okay. Are path variables or path quantities. So with all this understanding, now we are in a good state to understand one of the most important ideas, heat capacity. What is heat capacity? Take 1 mole of copper, let's say it is at 25 degrees Celsius, supply some heat so that it goes to 26 degrees Celsius. How much is the total amount of heat required? 25 joules. That is our case 1. 25 to 26 degrees Celsius, increasing 1 mole of copper's temperature, and for that this much amount of heat was required. Now if we heat it further and take it to temperature 27, we are going to give twice the amount of energy. So 2 into 25 joules. So if delta T is temperature increase, we can say the amount of heat required is proportional to the temperature increment that we are looking for. Now instead of copper, if we take 1 mole of nickel, again if it is at 25 degrees Celsius, heat it to bring it to 26 degrees Celsius. What is the amount of heat required? Is it 25 joules for this also? Answer is no. It is 26 joules. So obviously Q depends on material. So if Q depends on material and it is proportional to delta T, we can write this, and this C is going to be a constant depending on the material. So this constant C is Q by delta T. This constant C is Q by delta T, and this is called as heat capacity, amount of heat required to increase the temperature by a degree per unit temperature. What is the heat required? Now if pressure is constant in this process of supplying heat, then we call the heat capacity as Cp. If the volume is constant, we call it Cv. And units are going to be the amount of energy required joule per 1 mole of material per 1 degree Celsius or 1 Kelvin increment. So joule per mole per Kelvin, that is the unit for heat capacity. Okay. So between the Cp and Cv, heat capacity at constant pressure and constant volume, which one is higher? Which one is more? 1 mole of neon if we take, that is the gas in this 25 degrees Celsius. If we are going to keep the pressure constant and increase its temperature, how much of energy is required for this? That is question number 1. Then this is at constant P. Here at constant volume, how much of heat is required to bring it to 26 degrees Celsius? So which one will be higher? In both the cases delta T is 1 degree Celsius. For the constant pressure case, the heat required is 21 joules. Okay. Here it is only 13 joules. In both the cases, it goes from 25 to 26. So what has happened? Here in this constant pressure case, whatever heat we supplied has now done two things. One is increasing the temperature, other one is increasing the volume. The same heat has to do this work as well. Whereas in the constant volume case, there is no work. All the heat that we supplied has gone only to increase the temperature. So you can see 13 joules are enough to increase the temperature, but the extra 8 joules are given here to do the work when the pressure has to be maintained constant. Okay. So in that way, C depends on pressure and volume. Cp, which is Q by delta T at constant pressure. Cv is Q by delta T at constant volume. If we put it in a vanishingly small changes manner, then we can put this differential form for Cp and Cv. And this is going to be quite useful as we move forward. Since we saw that Q is proportional to delta T, can we say, based on this, that Cp versus T is a linear relation? The answer is no. It can look something like this: a plus bt plus ct power minus 2, possibly even some more terms also can be added. The curve looks like this, Cp versus T. It's not a straight line at all. You can see in the x-axis, two parts are marked. This is all same temperature increment. Okay. For same temperature increment here and here, you can see how much of energy is required. For this change here, you can see a more amount of Cp is there compared to this same amount of temperature increment here. Okay, you can see a very small Cp, delta Cp here. Okay. So this is how Cp versus T looks. Now, what is this heat capacity? Why do we call it heat capacity? Heat capacity is capacity to take in heat, right? So how is heat taken in? The energy is accommodated, right? In the kinetic energy of vibrations in solids, it is accommodated in solids. Okay, so when solids, if you see what happens inside, as more and more heat comes in, the solid atoms actually vibrate like this. Okay, this vibration happens, and the vibration happens in all three dimensions. So we call it degrees of freedom 3. Okay, so because it can, in this picture, it is moving like this. In this kind of x direction, it can also move in y direction and z direction also, right? So all three dimensions are possible. Therefore, we say degrees of freedom is 3. If more degrees of freedom are there in a system for atoms to take in heat, then it is going to take more heat. Okay, so heat capacity depends on these degrees of freedom, how the energy can be accommodated in the system. Instead of solid, if we think about other systems, the energy is accommodated in the kinetic energies of motions of particle constituents, such as translations, rotations, and vibrations. Okay, depends on the material. In gases, for example, translation happens like this. Atoms just move in space. This movement also requires energy. Heat can be taken, or heat can be accommodated in this form as well. And this is translation. Atoms can rotate, diatomic atoms like H2, N2 and all, they rotate like this. That is rotation. And vibration, as we see in the last slide. Okay, all of them have degrees of freedom. Translation can happen in all three directions. Rotation can happen with respect to what is the axis of rotation. Okay, vibration, we saw again 3 degrees of freedom are there. All these different degrees of freedom are going to accommodate the energy. So in that way, they contribute to heat capacity. Are those the only contributors to heat capacity? There are more. For example, heat capacity can also come from magnetism, magnetic heat capacity. And there are different phenomena here: magnetic spin waves, heavy fermion pairing, and magnetic ordering from para to ferro to antiferro to ferri. These are all magnetic dipoles arrangement. All these things are there, and Schottky anomaly, spin glass. Okay, I'm just telling the names of them. They're all subject matter of condensed matter physics. What is important is all of these effects accommodate energy and contribute to heat capacity. Okay, This magnetic heat capacity is quite important. If you think about magnetic systems such as iron, if you see how is the Cp versus T without magnetism, this is how it looks. But when the magnetism is added, it gets a different kind of magnetic contribution like this, okay, very different curve. So why we have to bother about it now is, as we go along, we'll be looking at modeling the system's thermodynamics. So their modeling Cp is going to be complex when the systems have magnetism. Okay, magnetism can be separately modeled and added to a model which has no magnetism in that. That's how we are going to model it. Right. Then what else can contribute to heat capacity? The volume expansion work. We saw in the case of Cp that when we heat a material, it can also do some work. So this volume expansion work is also a way of accommodating energy. So that is a contributor to heat capacity. Okay, volume expansion work occurs from the heat supplied. Hence, it contributes to heat capacity. Then, electronic heat capacity. Okay, free electrons are there. Excited electronic energy levels accommodate energy and contribute to heat capacity. In semiconductors, you might have come across, there are atoms which are not in the conduction band, but once some energy is given, they go to conduction band. So those are excited electronic energy levels. So for doing that, it requires heat. It requires energy, so they can also contribute to heat capacity in that way. Then phase transitions, they can also accommodate energy. For example, a solid transforming to liquid. All atoms are nicely bonded, all bonds are broken here, so that requires energy. So this is one way to accommodate energy. Okay. So what are all the heat capacity contributions we saw? Vibrational, translational, rotational, all these movements contribute to heat capacity. The work of volume change, electronic heat capacity, magnetic heat capacity, and energy of phase transitions. Okay, so that's about the heat capacity. Now we are at a very good point to understand one of the most important ideas, state properties, internal energy. What is internal energy? It is represented as U or E depending on the textbook that you see. Sum of all kinetic and potential energies of particle constituents. Okay, kinetic and potential energies of particle constituents. That's what internal energy is. We'll see about that in detail now. The kinetic part we will consider. The translation of monoatomic gases like neon is one kinetic energy of particle constituent. So that's going to be part of internal energy. And the rotation in diatomic gases, that's going to be part of internal energy. And the vibration in solids is going to be part of internal energy. And free electrons motion, electronic and magnetic contributions to internal energy, just like in the heat capacity, are all there as internal energy. Now what about the potential part? That is going to be different. To understand that, let us take an analogy. Consider a body within the Earth's gravitational field at some height m, and if it is under a force field, a gravitational field, therefore it is going to have some potential energy, right? mgh, we can calculate that. Now if we remove this partition, it's going to fall, coming to a lower potential energy, right? So minimum potential energy state is the stable state. That's the reason why it could not stay afloat. It has to fall down to achieve the minimum potential energy. So this happens within the field of gravity. So there is a force field. Important word is this force field. So within gravity, there is a potential energy. So if there is a force field, something can experience potential energy. That is important now. Okay, minimum potential energy state is the stable state for an object within the field of gravity. If you imagine a landscape like this, and any object where it can stay with the minimum potential energy, it's going to be here. Any other location, it's not going to be stable. Only here it will be stable. So minimum potential energy state is the stable state. Fairly straightforward. Now, this mass also has a gravitational field. According to Newtonian mechanics, it has a gravitational field. When if that is away from the gravitational field of Earth, they are not going to bother about each other. Only when they start to meet, they interact and the minimum potential energy state is achieved. Okay. So now if we want to look at the actual potential energy that is there in the internal energy, it is not due to gravity. Let's see what is that. Okay. Imagine an atom. So this, you can imagine atom electrons fluffing around and there is nucleus with proton and neutron. We are going to put it as a small dot like this. So this is an atom now. This atom, if you take, it has a force field around that. What is that force field? There's one more atom, a force field around that. This force field is electrostatic. Okay, you know what is that? Electrons and electrons repel, electrons and protons attract. That force is what we are talking about. It is an electrostatic force. So now when their force fields interact, they are going to come to a minimum potential energy state. Okay. So even this force field causes a potential energy and things go towards a minimum potential energy state. Quantum mechanics deals in an exhaustive way about this, how these electronic forces are getting balanced and how this minimum potential energy state is achieved. That is there in detail in quantum mechanics. But this is enough for us to proceed further. Minimum potential energy state is the stable state we said, and that is nothing but bond formation. Two atoms coming together and making a bond is nothing but they are reaching the minimum potential energy state. It's a beautiful idea. If you think about potential energy in y-axis and distance between the atoms in x-axis, when they are too far apart, they are not going to bother about each other. Therefore, the potential energy is zero. But as they come together, they are going to have a potential energy following this path. If they are closer like this, the potential energy goes down to some value like this. If they are at some sweet spot distance, they are going to have minimum potential energy. If they try to get closer than that, the potential energy is going to increase actually. So this is the bond length. This at this distance, they have the minimum potential energy. This curve is extremely important. As we go along, I may keep drawing this kind of curve in the class. So it means that you should recall this curve in your mind. And this is going to explain so many things about the materials. So it's quite important. Okay. So sum of all potential and kinetic and potential energies, the potential energy part is this bond energy associated with chemical bonds. So that's what potential energy is. Okay, in solids you can see atoms are nicely bonded. You can imagine why they are at that particular distance. Not closer, not far away. Because that is the distance which gives minimum potential energy. Right. So sum of all kinetic and potential energies of particle constituents is internal energy. So in this understanding, there may be some sources of error. If you think about a system like this, at some height, mgh1 you can use and calculate potential energy in external force field, for example, gravitational field. Is this part of internal energy? If you remove this partition, the system is going to fall. There is a kinetic energy for it and it achieves a new potential energy. Is this kinetic energy part of internal energy? So kinetic energy of the system as a whole or potential energy in the external force field. These are not internal energy. When we say internal energy, we talk about the potential energy and kinetic energy of particle constituents, not the system as a whole in an external gravity field or the movement of the body, the entire body and the kinetic energy associated with this. This is not part of internal energy. It's quite important. Okay. Another source of error is mass can be converted into energy according to E equals mc square. We call it mass energy equivalence from the theory of relativity. So any mass that disappears is going to give out energy, multiplying that mass with light's velocity squared. So it's going to be a huge amount of energy coming from even a small amount of mass. This is what happens in sun to produce energy. This is what happens in nuclear bombs. Okay, but this is not part of internal energy. In thermodynamics, what we deal as internal energy is not going to have this mass energy equivalence. Okay, a short summary of this is kinetic energy of free electrons, atoms and molecules is part of internal energy. Potential energy of chemical bonds is part of internal energy. Which are not part of internal energy? Kinetic energy of the system as a whole, potential energy inside any external force field such as gravity, and mass energy equivalence. These are not internal energy. Right. So let's see internal energy of an ideal gas. In ideal gas, only kinetic energy of atoms is the only contribution to internal energy because there are no bonds. Atoms are freely moving, so there is no contribution to internal energy from chemical bonds. It's only the kinetic energy part. If it is only kinetic energy, we have already seen this, half mv square for an atom is equal to 3 by 2 kT. We saw that temperature is a measure of kinetic energy based on this equation. If you want to calculate internal energy for n number of atoms, we are going to multiply this half mv square with n. That is going to be the internal energy for ideal gas. So we have derived this 3 by 2 n kT or 3 by 2 small n RT. All this is going to be internal energy only. And in terms of PV, we can write this nRT can be converted to PV. We can call U as 3 by 2 PV. And if temperature changes, you can see here, if temperature changes, then U is going to respond to that. If temperature changes, internal energy changes. Let's visualize internal energy as a state property in PV space. Two different, this is P1, V1, this is the state 1. This is how a gas looks with V1 and P1 as state variables. And P2, V2 is also represented here. This is going to be V2, P2. This is a new state. If between these two states system goes, internal energy is calculated by 3 by 2 PV. So for both the states, we can write internal energy like this. What if the system goes from state 1 to state 2? Internal energy is going to go from this value to this value. If system comes back from this value to if system comes back from state 2 to state 1, the internal energy is going to be reversed to the original value, right? That's why we call it state property. Change in a state property is zero in a cyclical process. We saw that previously. A state property does not change in a cyclical process. Okay, so that's why internal energy is a state property. A change in internal energy can be calculated using integration of du if we can track du. And over a cycle, if we do that, it's going to be zero. The visualization that we had for potential energy previously is now given for internal energy here. This is internal energy of state 1 and this is the internal energy of state 2, U1 and U2. If the system goes from here to here, this red color bar tells you what is the internal energy change. Can be calculated by integration C du. And if the system goes back to state 1, that change vanishes. Therefore, internal energy change over the cycle is going to be zero. If we put it in PV space and move from state 1 to state 2 in any path, the change between state 1 to state 2 is the same red color bar. Okay, it does not depend on the path. Okay, change in a state property does not vary due to the process path. It's an important feature of state properties. Right, we'll stop with that. Thank you. I hope the lecture is useful. See you in the next class.